morning. Ooh. Okay. Okay. Be just a moment, everyone. How are you today? That's good. Okay, hello. All right, hello, the three of you watching this live, welcome. I'm sure more people will drop in a little bit. Let's go ahead and get started. Now, I think we might be missing a PDF of today's slides. That's not great. Let me just load that in for us. Ooh, question about using Java libraries in assignments. Okay. We'll take a look at that in a little bit. And okay. All right, those are up. That's all good. Let's get started. So, turn on the Q&A. And All right, so let's just take a quick look at this question that's literally just popped up in my uni. Your implementation must not use any of the programs in build regular expression program. Cannot use Java regex or any other. Yes. Okay, so that's a question that's just popped into Piazza, so I may as well just answer it now, although I will answer this in text form in a little bit, or after today. Yeah, you're implementing a regex handling system from scratch, so naturally just using the one that's already built into the programming language is a no-go. The point here is to build a system that can take a regular expression, pass it into an epsilon NFA, and then evaluate that epsilon NFA. If you try to use Java's inbuilt regex handling library to handle regexes when you're trying to design a regex handling system from scratch, you will get a 0 for this assignment, and that should be self-evident. Or any other DS. I'm not sure what you mean by any other DS in this case. Basically, we're just using vanilla Java. You shouldn't need any other libraries in order to implement this. There are plenty of DS data structures. All of the stock data structures that are available in Java's standard libraries that come in the standard JDK should be sufficient enough to implement this. Yep, that's that. Should actually move on to the slides. Petrinets, we're looking at Petrinets this week. And same deal as usual, we have we have a number of examples that we're going to work through, and we'll go from there. We have the discussion in Echo 360. We have the live Q&A in Piazza if you want to ask any questions aside from the one that we just sort of answered then. And that's that. What's happening this week? Well, workshops are back on this week. That's about it. I've opened up and set up the submission portal for Programming Assignment 1. The submission portal is basically just going to validate that your stuff works insofar as it compiles and can be accepted by the system. And it's also going to do a couple of other basic checks. And I'll be adding a few more basic checks into it later this week to help give you some more feedback on your work. But at the moment, it's just a basic submission portal. Can we still use the Java regex as a reference to check output? Yes, you can absolutely use the Java regex library in your testing code to check output. That is a great question. And to be honest, that is how I'm going to be checking your code. I'm going to be, that will be one of the ways that I'm checking your code, is I'm going to be checking how it compares versus an actual proper regex implementation. Yeah. So yeah, not in your implementation, but absolutely in your testing. Go for it, by all means. Yeah, good question. Okay. So, well, discussion is about Petrinets this week, not really in More Machines. That was last week. Let's take a look at some examples. So, again, hopefully we've all read the notes on Petrinets and we have a rough idea of what's going on. So let's just start out with a couple of examples. We have this Petrinet right here that you can see on the right there, and we're going to take a look at firstly whether this system is safe. We'll check to see if a few different markings are available. Then we'll try and convert this down to a DFA. So first things first, is this system safe? Well, let's go ahead and find out if this system is safe or not. So should have printed this system out. That would have really helped. That's okay. And top corner there. Zoom this thing out. Come on, buddy. Almost there. Oh, it really doesn't want to today. Okay, there we go. And there. Okay. All right, so what does this system look like? So we've got okay, that all seems good. And that's an initial state as well. And any other initials? Yes, this one's initial. And then we have okay, and that is our basic pitch. Wow, I did not fit that on the page very well. Okay. All right, well, I'll just have to move it around a little bit, or maybe I can move this up a bit. Okay, moving this up a little bit worked. Let's not forget that and that. Okay. All right, so we have our Petrinets. And this is going to be make sure that we have our states properly. 3, 4, 5, 6, exactly where you think they would be. 3. Okay, that's an initial state. This is T1, T2, T3, T4, and T5. Okay. And that's all of that. All right. Cool. So let's start by remembering how this thing actually, how one of these actually works. So the way that a Petrinet is going to work is that we have a variety of states that we can be in. We have the transitions between those states, and in order for a transition to be able to occur, all of the inputs to the transition have to be satisfied. So a transition is not enabled, as we say, until all of its input conditions are satisfied. So let's just start out by figuring out what the initial state of this system is. Hopefully that should be fairly straightforward. We've got the arrows to indicate what the initial state of the system is, as so. We'll put these markers in there. And now we can start to take a look at what transitions are enabled. Remember, the whole idea with the Petrinet is that you have these transitions that we use to synchronize multiple different FSAs together. So we say, okay, let's put a barrier in place, essentially. That's what the transition represents, and say that we only allow a particular set of arrows to flow through, as it were, if all of the input conditions are met. So all of the input conditions are met when there is, when we are in each corresponding state the requisite amount of times for each arrow. So in this case, these arrows don't have any you can have multiple arrows going from one state to the same transition, and we represent this with like a little counter number. So in some cases you might require 2 in order to enter a particular, or in order to trigger a particular transition, and so on. So in this instance, let's just start by saying, okay, well, what transitions are enabled in this system? What transitions are enabled in this system right now? And while we're at it, what would we say that the marking of this system is as it stands? Going to ask that in the Q&A. All right, post that in Piazza. What do we think the initial marking of the system is? And to anyone, or in the discussion board, or whatever people want. They're magnetic and they slide. We'll just give people a couple minutes to see that. Any suggestions? Okay, all right. Okay, so the system is initialized into this configuration, so we say that the marking is, we have one token in state P1, we have one token in state P2, or place P2 rather, we have one token in place P5. One of the things about Petrinets, as you're hopefully already aware, is that in Petrinets we can be multiple times in a single place. So I could have 5 tokens in place P5, unlike in our basic NFAs or DFAs, where if you had a transition that took you from being into 2 separate states, so in like a DFA, or sorry, in an NFA, for instance, if you had this, and we were here and we got an A, in a basic DFA, that wouldn't cause us to be twice in this state here. It would just be, okay, 2 tokens leave, and we end up being in this state. We go from being in these 2 states to this one state. In a Petrinet, you can be in the same state multiple times. So in this instance, we denote that by saying, okay, well, we're in place 1 one time, we're in place 2 one time, and we're in place 5 one time. And we commonly write that as P1 is 1, P2 is 1, and P5 as 1. Or to write it out an even longer way, you would say, you would write out each place in the Petrinet and its corresponding marking. So you would say P1 is 1, P2 is 1, P3 is 0, P4 is 0, P5 is 1, and P6 is 0. So we write it out like that, and I've just posted that in Piazza. So a shorthand way of writing that is, and this only sort of works when you go in, when you're working with single digits. If you get up into like 10 or more in a particular state, that's when you kind of need this long-handed way of writing it. But we have a shorthand way of writing that, and that would be, there are 6 states, so it would be 1, 1, 0, 0, 1, 0. Now, if we were, well, if that happens, then that would represent something like 0, 2, 0, 0, 1, 0. So that represents 0 in place 1, 2 in place 2, 0 in place 3, 0 in place 4, 1 in place 5, 0 in place 6. So a couple different ways of writing down the initial marking. This is the sort of shorter way where I've left the zeros out, but generally we want to include all of the states. So I've written the long way in, or the longhand way in Piazza there. Okay, so initial state is like this. If we take a look, which transitions are enabled in this system? Can we have a guess as to which transitions are enabled? Yeah, so we'll start at the top. Remember, a transition is enabled if all of its inputs are satisfied. So transition 1, in order to be enabled, you need to have a token, or you need to be in place P1 and in place P2, because you have these 2 arrows coming from place P1 and P2. So would we say transition 1 is enabled, yes or no? Yeah, so transition 1 is enabled because we are in state P1, or place P1 and P2. Those satisfy the 2 input conditions for the transition. So transition T1 is enabled. Let's take a look at the other transitions. This should be fairly quick. Transition T2 is not enabled because there is no token in place P3, and therefore its input condition is not satisfied. Transition T3 is not enabled because there's no token in place P4, therefore its input condition is not satisfied. Transition T4 is not enabled, even though its input condition, that being place P5 here, is satisfied. The other input condition from place P4 is not satisfied, so you need both P4 and P5 for transition 4 to be enabled. And similarly, transition 5, well, we need both P4 and P6 for that to be enabled. And with that in mind, let's go ahead and see what we can do here. So just double check that I've got the logic for this right. Oh, that was a 2. There was a sneaky 2 here that I missed. Okay, that's a 2. Can't forget that. All right. The 2 is important because this represents 2 outbound arrows from transition T1 to place P3, which means that when the input conditions are satisfied, you're going to result in 1 token coming out and returning back here, 1 token leaving here, and 2 tokens entering here. So we actually end up with 3 tokens when we previously only had 2. Let's go ahead and fire transition T1 and see what we end up with. So We fire transition T1, both of the input conditions are satisfied, then we fill out all of the outputs. So we fill this output, that's going to leave us in place P1, and we fill this output, and this output has 2, so that's going to put us in place P3 twice. Okay, and what transitions are currently enabled in this system? Well, transition T1 is no longer enabled because its input condition of P2 is not satisfied. So let's take a look at the other transitions. T3 is not enabled, T5 is not enabled, T4 is not enabled, T2 is enabled, so we can go ahead and fire that one. And we end up in this configuration here. Now we have a couple different options. T2 is still enabled, and we could fire T2 optionally at this point, and we would end up here. Or we could fire T3 at this point, and we would end up here, back where we started. So T2, if we were to fire T2 twice, we would end up here, and anytime there's a token in place P4, T4 is enabled. So if we were in this configuration here, we could fire T4, that would have both of these input conditions satisfied and result in both of these outputs, and we'd end up in this configuration. Are there any other transitions that are enabled at this point? T2 is enabled, so we could shift down here. Now at this point we have a couple options. T4 is enabled and T5 is enabled. What happens if we fire transition T5? Any ideas? That's okay. Okay, well, if we fire transition T5, its two input conditions are satisfied, so it takes these two inputs and it produces one output. We end up back in our initial state where we were before. That's all very convenient. Not all Petri nets are nice and neat like this. Let's take another look now. If we were to, back where we were a second ago, if we were to fire transition T4, where would that put us? Well, that would work because you can see that the input conditions of P4 and P5 are enabled. So we take those, we bring them back, and we end up here. Now, are any transitions enabled in this configuration? I'll triple check that this is all working properly because yes it is, okay. Right, in this configuration, let's see, transition 1, it's not enabled because its input condition from P2 is not satisfied. Transition 2 is not enabled, its input condition from P3 is not satisfied. Transition 3 is not enabled, its input from P4 is not satisfied. Transition 5 is not enabled because its input condition from P4 is not satisfied. And the same goes for transition 4 here. It is not enabled because its input condition from P4 is not satisfied. So we've actually reached a state where the system, there are no enabled transitions. Therefore, the system is in what we call deadlock at this point in time. So this system is deadlocked, it can't move. But we've just played through all of the possible configurations in this system, so we know that there's probably about 6, 7, 8 maybe different potential states that this system could be in, depending on what actions we take at various different points in time. So we know that this system works, and so follow-up question, is this system safe according to the definition of B safety? Come on, people watching at home, I know there's 7 of you there. I see you there. Imagine if someone fell asleep and they just heard me say, I see you there. Anyway. Is this system safe? We can't know for certain, but we can probably take a guess, but a good way to determine whether the system is safe or not is to try and turn it into a DFA. In general, safety or a system is considered B safe if there exists a number B for which, or N safe depending on what you go with, but if there exists a number B for which no value in any part of the marking exceeds that value B. So, for example, the system is 1 safe if at most you see 1 token in any of these places at any given time. A system is 2 safe if at most you'll see 2 tokens in any place at any given time. In general, the system is considered safe if there exists a number that we can say, okay, we're not going to go above this number. If there doesn't exist a number, then we are in an unsafe system. Let's try mapping this out to a DFA, and then we can see what we end up with. So the way that we map this out to a DFA is much the same way that we do with an NFA, and that is to say we play the system out from the start, and we treat every combination of places, or every unique marking, as a unique state within the system. So I'm going to use the shorthand notation for this. We're going to start off in a once in P1, once in P2, once in P5. 1, 1, 0, 0, 1, 0. That's going to be our initial state in our DFA conversion of this system. And then we just look at, and then we just play the system through. We play through all of the possible transitions that could occur. So what transitions are enabled in this configuration? Only T1. So let's go ahead and add a T1 transition here. And where is that going to put us? With magnetic tokens sticking together really hard. That's going to put us into this configuration here, which is going to look a little something like 1, 0. This is P3. 2, 0, 1, 0. So that's that there. What transitions are enabled at this point? Just T2. So let's take a T2. And that's going to put us into this configuration. 1, 0, 1, 1, 1, 0, like so. And now we have 2 options at this point. We have another T2 or we have a T3. So I'm going to add both of those in. So if we were to take a T2, we would end up in this configuration here. 1, 0, 0, 2, 1, 0. Like so. If we were to take T3 at that point, well actually that just takes us back to here. So like so. And if we were to take T3 from this point here, sorry, from this point here, then that takes us back to here. Okay. So once we're in this configuration, we can also take a T4 for that matter. So I'm going to add T4. Things get a little bit messy. T4 would put us into this configuration here. 1, 0, 1, 0, 1, 1. And if we're in this configuration, we can take a T2. T2 is going to put us here, which is going to be... Didn't plan this out very well. That's okay. These things happen. Let's go back up here. Like so. And then we have some options here. We can either take a T3, and a T3 is going to put us back to here, which is right where we came from. So we can see that all of these ones can float back with the T3. We can take a T4, which is going to put us into this configuration here. Like so, which is that dead end that we were looking at just before. Or we can take a T5 from this configuration here, and that's going to put us back to the initial state. I think that's just about everything. So we can see that this is a nice closed system. It doesn't run away forever. Something to watch out for is systems that do run away forever, because they do exist, and we'll take a look at one of those in just a moment. So we can say that this system is safe because it doesn't run away forever, which is nice. And we can say specifically that it is not 1 safe because the number 1 does get exceeded in this marking, but it is 2 safe. We do have a maximum value of 2 in these places here. And that's the DFA that we get from this system. So Petronet, like an NFA, just play it out, and you can end up with a DFA. You just have to watch out for the possibility of things running away. Let's take a look at another example. Does anyone have any questions about that example that they want to ask, either in Piazza or in the discussion, or just right now? Just give people a moment to ask questions. All right, let's take a look at this one then. So no. I'll switch back to the dot camera in a second, people. I know that we're there. Okay. All right, so there's that system. Let's take a look at the initial marking of the system. We need more markers probably. Oh, that's probably okay. 1, 2, 3, 4. And there weren't any sneaky 2s in there somewhere. Nope, no sneaky 2s. Okay, and this was T1. T2, T3, and T4. Okay. So there's our basic system to start with. Let's just start by taking a look at which transitions are enabled. So in this case, you can see that the arrows are actually sort of coming in from both directions on several of these transitions. So T1 is enabled because both of its input conditions are satisfied. T2 is also enabled because both of its input conditions are satisfied. T3 is not enabled because its P3 condition is not satisfied, and T4 is not enabled because its P4 condition is not satisfied. So again, a couple things. What's the initial marking of this system? We want to know if the system is safe, and we want to see if we can get a DFA out of this thing. So let's go ahead and start off. What do we think the initial marking is? Come on, people, we've seen it in the previous one. Let's switch back to the other screen. I'm actually going to give us a few minutes to have a go at this one ourselves before we dive into it in too much detail. So, what is the initial marking of this system, and is this system safe? And if so, if not, why or why not? And I put those questions in Piazza. Take a moment, draw it out if you need to, play it through to see what you end up with. Was the initial example of, what's the initial marking example 2? Yeah, all right, I'm seeing some answers popping up. Yeah, so one of the things to be aware of is that we cannot just say P1, P2, P5, P6 in this instance. If we just say P1, P2, P5, P6, it's like, okay, but how many in P1, how many in P2, how many times are we in place 1, how many times are we in place 2, how many times are we in place 3, and so on and so forth. Yeah, so we do want to, with the PetriNet, explicitly specify with number representations of how many times we are in each particular state. So in this particular instance, we say P1 is 1, P2 is 1, P3 is 0, P4 is 0, P5 is 1, and P6 is 1. Yeah. Okay, so we're saying it looks like it's safe so far. Oh wait, that was a note, not a question. Oh. It's supposed to be a question. Convert this to a question. There we go. All right, that's better. It's supposed to be a question. What do we think, people? Is this one safe? Just so we've got so far we've got 1 vote for it seems like it's safe. In fact, I'm going to turn this into a poll if I can. Let me see. And that question note. Delete that. Let's try this again as a poll. Okay. All right, making it a poll. Let's have a, yeah, I know the content section is empty. Okay, so I've added a poll in there. Have a think, play it through a little bit. It'll give us a couple more minutes to play this system through and see what we end up with. And that's convenient timing because there's a stream of fire trucks coming down Pulteney Street at the moment, so... Well, there's just one. Usually there's like 5. We'll see. Let's start playing this one through, and we'll give people some time to enter in their poll choices, whether you think this is safe or unsafe, or some variation of safe. Okay, so we have a few different options that we can go with. We'll just do like a very quick playthrough of this system to get a feel for how it's going to function. So let's take a look at what transitions are enabled. Right now we have T1 enabled and we have T2 enabled. So I'm going to take transition T1 because T1 comes first. And what's that going to result in? Well, it's going to pull this input, it's going to pull this input, and it's going to then result in this output and this output. So we end up in this situation here. Now, which transitions are enabled? Well, we have T2 is enabled and T1 is not enabled because we're missing P2. T3 is now enabled because this input condition is satisfied here. So let's take a look at that. So let's try T2. So takes this one, results in this situation here. I need to double check that I haven't missed something in this diagram. No, that's all okay. All right. So we are in this configuration here. And which transitions are enabled? Well, we know T3 is enabled. So if I take T3, we end up in this situation here. And we know that T4 is enabled at the moment, and T1 is enabled again. So if we wanted to, we could cycle that again if we wanted to. T4 is enabled because P4 is satisfied. So that would result in this configuration here. It's like, okay, well that's basically where we started again. Let's play this around a little bit more. I'm going to take T2 again, and I'm going to take T4 again, and we're going to end up with something like this. Interesting. Now, if I were to take T4, and we're like, okay, so maybe it's just a two-state system. Now, what if I were to take T2 again, and I then took T4 again? So that's what T2 was, yeah. So we end up back here again. And it turns out that if I take a cycle of T2 followed by T4, we're going to end up in a situation where the number of markers in here is just going to grow and grow. And if we tried to map this out as a DFA, and let's actually try to map this out as a DFA, or at least we're just going to we're going to see where we end up with this if we try. It's not going to be a fun time. Okay, so if I start in our initial marking of, put those away, 1 1 0 0 1 1, and if I did a T2, then that's going to put me in 1 1 0 1 0 1. Okay, and then if I did T4, then that's going to result in, shouldn't have made them magnetic, oh dear. Okay, all right, if I did T4, that's going to result in 1 1 0 0 1 2. The way that we can tell if a system is going to be unsafe as we are trying to evaluate it is if there exists a marking, we can say as a general rule, if there exists a marking in your Petri net that is exactly the same as a previous marking, except any one or more of the numbers are larger. So yeah, you'd say, yeah, if there exists a marking in the Petri net where any one of the place values is, where all of the place values are the same or higher than another marking that already exists, then that means that there is a potential for one of the values to grow to infinity. And we would say that this system is unsafe. And if we were to keep playing T2, T4, this would just go on forever. We would never actually get a DFA because this system is not capable of being deterministic, because it will just go on forever. So you wouldn't actually, so when we say, how do we convert this to a DFA? The answer is you don't convert this to a DFA. Don't. There's a trick question, people. You can't convert this to a DFA. It goes forever. This system is unsafe. So that's something we need to be careful of and aware of when we are working with Petri nets. In your next assignment, you are going to be working with Petri nets, and you are going to need to design systems. Your systems should inherently, by their design, be safe, but you need to be aware that it is possible, if you design your systems incorrectly, that they could end up being unsafe, and we want to avoid unsafe Petri nets. Okay. Third example question. All right, we've been asked to design the control logic for a conveyor belt system. And this is where like the whole safety thing comes into play. For example, if you're designing a conveyor belt system that can ideally only fit X number of products on it at a certain time, and you design a system where you are not properly accounting for those, you can end up with like this build-up of products on the conveyor belt indefinitely. That's probably a bad thing. So let's say we're building the control logic for a conveyor belt system. We just want something really basic though. We want a simple belt. We don't particularly care about, we don't even necessarily care about safety in this system, though we might take a look at safety in just a moment. But we're trying to build a conveyor belt, and it has 3 different input lines. It has 3 different output lines. It's like a shared section. So basically we want to control access to a shared section of this conveyor belt. So if I were to draw what that might look like, that could look something like, we have and so, we have our rollers or whatnot on the conveyor belt system, and let's say it moves in this direction. So we have a conveyor belt, and products come along. And let's say we have 3 different types of products. Conveniently, we have white products, blue products, and red products, just for argument's sake. And so your products are going to move along the conveyor belt, but for whatever reason in this particular configuration, let's just suppose that we can only have one type on this shared section at any given time. So if there are red products along here, the white ones and the blue ones, they're going to have to wait till the red ones leave, and then maybe the white ones can come through, and maybe the blue ones can come through. So we have this hypothetical conveyor belt system here. How might we design the control logic for a system like this, where we want to be moving all the different bits and pieces around? We want to control when they can or cannot move. Petri nets can be a good way of designing this kind of control logic. So let's take a look, and this is a genuine real-life practical application of Petri nets. They do get used in this way. How might we design a system like this? Well, the fact that we have these transitions that have to be activated by a series of input conditions lends itself to the type of system that we're designing. So we can build some basic structures to say, okay, well, we have a supply of products coming in. For our sake, we can start with like an abstract system where we can say, okay, well, we have a supply of products coming in. Let's say that we have a place here, and this place represents the empty section of conveyor belt. Let's say this is the shared section that we're actually interested in, and so ideally what we want is we want to make sure that the transition into this section we would have, in theory, 3 transitions in and 3 transitions out of this section. And ideally we want to have some way to say, okay, well, is this section of conveyor belt actually full or not? So what I'm going to do is I'm going to actually have 2 places and I am going to initialize the system in this configuration. So I'm going to say, well, okay, let's assume that the conveyor belt is empty to start with. That makes the most sense. Conveyor belt is empty to start with. And whenever something comes, whenever a product wants to enter the conveyor belt, it's going to have to check, okay, is the conveyor belt empty? So if this is a product coming in from line A, or from a given line, an input condition might be that the conveyor belt is actually empty to start with, and the same could go for all of these. So all of these transitions require the conveyor belt to be in the empty state to be able to fire. They also need to have, let's say that these states here represent products that are waiting to, or these places represent products that are waiting to enter this shared section of conveyor belt. So they would go in like this. And then what we can do is we can connect it up like so. Gets a little bit messy, I know. All right, what did we just do? So let's say that a product enters, each of these 3 sections. What have we just created? So we have a product in each of these 3 lines. We've created a system where we know that only one transition can ever fire at once. And at the moment, which of these transitions are enabled? All of them are enabled, yeah? We have the input conditions for this transition are met, the input conditions for this transition are met, the input conditions for this transition are met. But as soon as I fire any one of these 3 transitions, so let's say I take a product from the red line and I put that onto my conveyor belt, this condition is no longer fulfilled, therefore these transitions are now no longer enabled. And until we get a token back in here, and this represents the conveyor belt being empty, so until the conveyor belt sort of re-enters this empty place, these transitions are not going to be able to fire. So then it's worth noting there isn't any control logic in here about specifically where to send each different type of input yet. There could be more control logic for that. But arguably, these transitions here like so, any one of them could fire, and then we want it to occur that when one of these transition fires, it's going to replace the token into the empty state. So that is exactly what we're going to do, like so. So if we're in this configuration here, let's say this transition fires here, that's going to result in us being back here. The conveyor belt is empty at this point in time, which is nice. And then that allows the conveyor belt to now accept another product from another product line. Now, we could modify this if we wanted so that, for example, it was only going to accept products from this middle line here until it was completely empty, at which point it might accept products from one of the other lines, for instance. And there are a variety of different ways that we could build in that sort of control logic if we wanted to. So how might we go about doing that? What we might need to do in that instance is actually have so we have our full place here, and then we might need a empty place for each of the corresponding inputs. So okay, and something like this. And we would initialize the system like so. And we would also require control logic can be tricky. This is tricky stuff. Okay, so system would initialize like this. And we need to keep track of how many tokens enter and how many tokens leave. Just going to go back over here for a second. Let's think about this a little bit more before we try drawing it out, because again, control logic can be tricky stuff when you're implementing it this way. It's worth noting that the reason why we might take a more complicated approach like a structured Petri net or something to building out control logic of this type is because it provides the structure. That doesn't necessarily mean that it is going to give us like the most convenient or nice structure to be working with when we're developing our control logic, but it does allow us to map out the control logic and then also make sure that it is planned out in such a way that we always have a safe system, and that's part of the reason why we have Petri nets in the first place, or at least it's planned out in such a way that we have a robust system, even if it is a somewhat convoluted system. That's the reason why we're doing this. All right, so we need to have some sort of mechanism whereby when a particular transition is taken, then that is going to enable further entries from that particular state. So maybe we need an additional transition for that. I'm going to add a red one in here. So we might want something like this, where the input condition becomes fulfilled by this triggering. So I'm going to add it here. So we have this, and this is going to trigger. So now as soon as one has entered from this particular channel, that is then going to enable this transition to occur. and this transition can keep looping back on itself, like so. So that's going to loop back, so that's going to keep itself active. And that's going to slowly count up. Now this is unsafe in the context of the Petri net because it's going to allow for an unlimited number of tokens to enter into this system here. So we could put a limit on it if we wanted to. We would also need to provide a mechanism on the other side so that every time a token leaves this one here, or every time this transition is triggered, it's also going to be extracting a token from here. And actually this allows us to do that particular routing control logic. So we would also potentially say that we need that. I think that actually works. Let's play it out just to see what happens there. It's a bit of a complicated piece of logic in the diagram there, but you know, let's give it a go. So we didn't actually need that to be initialized to start with, but we say, okay, well the system is empty to begin with. Let's say that a token comes along here. Now at the moment this is empty, so we cannot follow this transition here. However, when this token passes into full, this is no longer empty, so the section is now locked down for only ones coming in from this middle lane here. The top and bottom lanes are not going to work for us in this configuration. And because this transition has occurred, that's also going to put a marker in here. That now enables this alternate transition, and that allows us to put another one into here, which would in turn result in another marker going in here. And at this point we have two markers in here, two dots in there. So if we take one in there, that would result in this one going away. And then if we take that would put one back here though. So that's a little bit concerning. We do still need to deal with the fact that that populates that. So we're like 70% of the way there at the moment. Let's take a look at how could we address that being empty. That always take out of there, that always take out of there. If anyone has any ideas in the audience, feel free to throw them in. Getting a nice ambulance break here. So the issue that we have at the moment, for those of you who haven't recognized it, is that every time we leave this state, that's going to get rid of that, but that's also going to result in us being here multiple times. So we want to restrict this to only being once. So One of the research papers that I'll be putting up has a solution to this, and it's actually a something that they call a negative transition, or I'll make the research paper on this available. So creating some of these control structures can be quite tricky within the boundaries of the Petri net as per the course notes. So they have created some additional, more complex variations on Petri nets that allow us to have transitions where a certain condition must not be fulfilled. So as opposed to where a certain condition must be fulfilled, certain condition must not be fulfilled. So making sure that a cell is empty. That drastically simplifies the creation of a system like this, because the diagram itself becomes a lot less complex. However, the actual development of the code to match the system does become a bit more complex. I'm going to leave this one as a bit of a challenge, I think, for all of us, and we'll have a play around with this a little bit more in workshops this week, so as to not waste any more time on it here. Let's have a play with how we can represent a Petri net system like this in actual code, because we know how to convert it to a DFA, which is good, but how do we deal with a system that is potentially unsafe? So we have to put extra protections in place in terms of a system that is unsafe, but how might we code up a system like this? One of the nice things about a Petri net is that you have this idea of the marking, which we have this idea of a marking. So for example, you know, P1 is 1, P2 is 1, something like this. We have this marking, that's all well and good. And then we have these different transitions, and a transition has a set of input conditions and a set of outputs that it requires. So one way that you could represent a transition is you could represent a transition as the set of inputs that it requires and the set of outputs that it requires. So we can say, you know, T1 is, we can represent this effectively as a matrix. So it's going to be P1 as -1. So if transition 1 required P1, then you'd say, okay, well, P1 is -2, and if it didn't require anything from P2, then P2 is 0. It's like, okay, well, that's all well and nice. That's the input conditions. And then the outputs, so if the system was literally just this was our system here, and we initialized like so, then that's that, and T1 just takes 1 away from P1, and in fact we can either represent this as a single dimension array where it just gives us the net number that we have to deal with, so or we can deal with it as 2 separate ones. 2 separate ones is probably preferable, so then the second line would be the outputs. So it's a P1 0, P2 +1. That gives us a lot of flexibility, and then that would say, okay, well, the input conditions are we subtract 1 from P1, or we could leave the input conditions positive depending on how we want, and we perform a subtraction. That might even be a bit better. I'm just going to cross that out. So that's the input conditions, and then the output gives us this. And if we represent this in code, what we can end up with is we can end up with a 2-dimensional array of the inputs and the outputs, which is something like this. We could represent this in code using whatever data structure you wanted. And then in order to action the Petri net, we just have to keep track of the current marking of the system as a one-dimensional array. So the initial marking of the system is this. And then we could apply each transition to the marking at every single step. And it's as simple as that. So we would take the inputs, we would have to check to see that all of the input conditions are satisfied, but you could loop over this row, for instance, and say, okay, well, how does that align with these? And then if that's good, then you would subtract this row from this row, and then you would add this row to this row, and that's it. And that's as complex as the code has to be. It can be a very simple matrix representation. You can go a bit more complex with objects and bits and pieces if you wanted to, but that's your basic kind of data structure that you need to represent a Petri net. So the control logic itself can be quite complex to design, but then the actual implementation in the programming can be quite a straightforward data structure to implement in the context of your programs. So that's how we might approach a programming side of things in terms of programming a straight Petri net as opposed to trying to convert to a DFA. Of course, there is always the option of converting it to a DFA and representing it as a DFA, but you also have this very straightforward object or array sort of matrix representation that you can apply to your Petri nets to implement them. And I think that's part of the appeal as to why they have been used and do get used in control logic in this way. Okay. Does anyone have any questions that they would like to ask for the remainder of this session? I am going to throw this one up for a bit of a challenge in this week's workshop, and we'll have a play around with that a little bit more, because the control logic can always be a bit of a challenge to get done. Yep, if anyone has any other questions, feel free to ask them now. Otherwise, that's where we're going to call it for today. All right, thanks a lot, everybody. We'll see you in workshops this week. Otherwise, we'll see you same time next week.